The largest of the Rota-beams by Whelen, the Rota-beam Commander, was a 4-seal beam oscillating beacon that boasted a 205-degree sweep, allowing it to display up to 3 colors in any given direction. This is a significant increase from models offered by the competition, and I've gone through this light before, and I think everybody that follows this sort of thing knows that I claim to have the last one, possibly somewhat dubiously, and I also claim it to be far superior to anything else offered at the time or since as far as an oscillating beacon. We know that it debuted around 1965 or 66, and we know that they were talking about the significance of the arc and the large oscillation distance, and we know that it disappeared within a few years and was never very popular and was never really adopted. But we don't know a whole lot about it aside from the fact of things that we can gain from my example. The 205 degrees of oscillation is really the claim to fame. We've been over that before, but I've never really delved into how does it do that and why didn't other lights of the time do that. The 174, which is also a really interesting specimen from Federal Signal, was also not incredibly popular, but it was the other major oscillating beacon, and you got about maybe 90 degrees of oscillation from it, which to me makes it not quite as advantageous. Even under a clear dome, you would only see 2 colors at any given point max. It's a cool sort of flash effect, but it isn't giving you the multiple colors. Like the Rota-beam Commander would give you the up to 3 colors in any given direction, and you could pick what colors faced what side of the vehicle. Again, everybody knows that I think this is really, really cool and a huge deal. But apparently the consumers at the time did not feel it was that big a deal, as neither were popular, especially this one.
It doesn't. It is, actually.
So the video today is going to go over the mechanism that made this long travel possible and explore some of my theories leading up to actually discovering how it works. This started with me making a couple observations about the light and making a couple guesses, which weren't exactly on target, but were interesting theories. So that's what this video is going to go over, is those particular theories and then the truth about the mechanism. When looking at the light and trying to figure out how it worked, I went off on a bit of a tangent as far as my theories as to how we achieved the larger oscillating sweep. I saw these 2 little protrusions on the bottom, and I thought those looked a lot like the contacts to an antenna, a through-roof mount antenna. And I thought they corresponded pretty closely to the point where contacts would cause it to reverse by electrical polarity. And I had just worked on a video about the Stingray by Code 3, which does just that. The oscillation feature of the Stingray is achieved by reversing polarity on the DC motor. And while this gave the Stingray multiple modes by means of contacts, and the Rota-beam Commander doesn't have multiple modes, those little protrusions I thought corresponded pretty well with where the contacts would need to be to achieve oscillation by reversing polarity on the motor. So not only had my judgment been kind of clouded by working on the Stingray project so much, I also kind of wanted it to be something cool and innovative and interesting. And so I started to try to come up with a method by which this would work. The experimenting I did with lights for my Stingray project, I thought applied, and in my mind I pictured contacts inside of the housing that would essentially cause a connection that would reverse polarity. And because the Stingray was able to do this so easily with minimal electronic components, I felt that this could be accomplished with simply switch relay sort of combinations in a solid state sort of device housed inside that housing that we could see. And because I didn't really want to take it apart, I was going off my observations. And as I said, my observations were most certainly clouded by my work on the Stingray video. Yeah, why look for the simplest, most obvious solution when the solution I want to find is far more interesting? And so that's where it kind of went. I posted a thread on e-light bars, and I floated some ideas. And then I had a couple other goofy ideas, which were atypical gearings that would cause rotational motion to be switched into oscillating motion. And with the round nature of the gearbox, in my mind, I had this kind of picture of something really special, really different, really odd. And so I dreamed up the, if not the polarity reversal, then absolutely some sort of atypical nesting set of gears that would just make this the most innovative and interesting mechanism we've seen on a beacon at that time. And so this kind of grew inside my head until a couple of people in the community sort of politely shot me down, which was nice of them, but it also caused me to look into it a little bit more, which is always a good thing. So I looked to Whelen's more contemporary oscillating devices, and I considered the Scotch yoke approach, which is what is used in the oscillating components in the Advantage Plus, Super Advantage Plus, and then also in the Pierce Alert. I think it's an interesting way to change rotational motion into reciprocating motion. It worked very well in the products where they used it. And so I considered whether this might be what was going on there. It seems possible, but it also seems like perhaps the space didn't really lend itself to it. At least that's what I was led to believe based on what I could see poking through to the bottom. And it didn't explain those protrusions. But nonetheless, the Scotch yoke or half Scotch yoke essentially served Whelen pretty well. And it is still an interesting design. And so I played around with all of the Whelen devices that I could find that used it. And I pretty well convinced myself that that wasn't the only mechanism, as you really still only got about 90 degrees of oscillation. The gear ratio could help with that. Theoretically, depending on the size of the drive gear on the base of the light head, that can be altered a little bit, but I still didn't think it was explaining the 205 degree arc. So I kind of decided this probably wasn't the only mechanism, if it was a mechanism. So looking back further, I found that the 6000 series oscillating bar advertised a 4-bar linkage system, which can be achieved with a round gear and linkage as well, much like the 174 beacon ray. That's how it does it. And also Whelen has done this. The intersection sweeps on the Delta Independence light bar are a bar linkage assembly. It's again about a 90 to 100 degree arc generally, which can be augmented a little bit with where your angles of linkage are, but you really don't beat the 100-ish degree mark, and there are mathematical calculations for that, but you top out is the point. This wasn't going to explain the 205 degree arc by any means, even though it is a popular solution to turning rotational motion into reciprocating motion. And Whelen wasn't the only company that used a bar linkage system. Federal Signal used it. Code 3 used it on their intersection lights. This is a Vista intersection light. It uses a type of bar linkage. Federal Signal certainly used a linkage bar in other products as well, including the oscillating assemblies inside of their V-shaped light bars that were not smart pods, and in their oscillating Firebeam and Sentry models, as well as the intersection sweeps in the Street Hawk light bar. So that this is a viable solution, but it still, again, only gets you about that 90 to 100 degree mark generally. So I set out to look for specifically 180 degree oscillation, or mechanisms that would give you over the 100 degree-ish mark. And I found what I call the wedge gear, because I choose not to pronounce the other word for it. The wedge gear scenario, where you have a large gear or portion of a gear driving a small gear. And that can actually be powered by a bar linkage system. We saw that in my Grimes light. You had a bar linkage system powering a wedge gear, which then drove a secondary gear on the actual light head assembly. So you kind of got the best of both worlds there. You could use your linkage assembly, but then you could use mechanical advantage or gear ratios to get a wider sweep than just the 100 degrees you would get directly from the linkage. If you haven't seen the video I did on the Grimes light, it's interesting, I think, and it does talk about sort of the same principles. The Grimes light, it should be noted, uses about a 1-to-1 ratio. That means it has the same sized gear on the light head as it does on the drive side or the bar linkage side. It should be noted, though, that if you change your gear sizes, you do get a gear ratio. So if you put a large gear on the wedge side or the drive linkage side and a small gear on the reflector side, you could theoretically get a much larger arc, which led me to believe I might be onto something. And it also led other people on the forum to think the same thing. eLightBars user R485, or Dr. Frankenstrobe on YouTube, thought this wedge idea was probably where it was at, and caused me to play around with some gear simulators, and I found that if you considered the gear on the left to be the drive, and even if it only was a wedge shape and you ignored the other teeth, and you made the gear on the right the light head side, you could get a significant increase in your travel on the smaller gear and therefore get more oscillation. So the combination of the bar linkage with the gear reduction, wedge gear if you will, was really starting to look like a forerunner for how this was accomplished. It wasn't as interesting, but it seemed a lot more practical. So ultimately, I was forced to see horses instead of zebras and consider the way that this actually might work. And I looked at the fact that around the time this light came out, Whelen was a primarily aviation company, and so I looked to other aviation lights. The Grimes light was an aviation light, and this other model of Grimes light, also for aviation. The design of that led me to consider the combination of the bar linkage and the gear ratio system. In this case, you have a large round gear, not a wedge, but it's the same concept, being driven by a bar linkage, and it's causing pretty significant oscillation on the smaller gears. This sort of system could conceivably give you quite a bit of arc and oscillation, and could also fit inside the Rota-beam Commander's housing. Really the only thing that I wasn't 100% sure on was how we accounted for the little nubs that I thought were electrical contacts. But all logic was saying that this sort of design was present in the aircraft industry at the time, was viable, and was most likely to produce the results we were seeing. So I started to accept the idea that I wasn't seeing some sort of magic breakthrough in the Rota-beam commander. So I re-examined the base of the light, and those little nubs didn't really look like electrical contacts the more I looked at them. In fact, they just looked like they might be pivot points for a gear system. So with that in mind, what do I have to work with? If those are pivot points for a gear system, which they definitely look to be, what did that mean for what was going on inside the light? Well, a theory was developed by watching what they did. You can see we have rotational motion on the orange. We have about 90 degrees of oscillation on the green, and then we have the full 205 degrees on the output shaft going up to the lights. So this was the mechanism we're working with. We know now that we've got a motor that's rotational, the orange nub or the orange spindle that is rotational, a narrow arc on the green, and a wide arc on the output. So working with that information, we were able to develop a little bit better theory about what might actually be happening inside. And this kind of shows the arcs that we were seeing. And that was applied by 485 R485 again to make this idea. So rather than tear the thing apart, I got the inspection cam inside, and I found that things were very close to his theory. What we didn't quite get was that the little spindles that were sticking out were not the only points of contact. They were just the only ones that were suspended. So where the linkage bar crosses the gears, you couldn't have contact going all the way through. You had to suspend the gears from one side of the housing, which is why those nubs were the only thing really showing through, because they were a more robust pivot point for the drive gear and the receiving gear of the linkage bar. And then that the gear from the linkage bar was in fact driving the drivetrain or the main spindle of the light. Unfortunately, taking the light apart isn't going to be an option. So illustrating exactly how this works, unfortunately, is best done through a little bit of modeling and this not so great inspection cam video, but I think it does show proof of concept. You will note that the both gears here are round. There's no wedge gear, but the gear does oscillate instead of rotate. There's no reason to make it a wedge, even though you're only using the teeth on a small portion of it. There's no reason to make a wedge if you already have a 360 degree gear. You're just not going to fully utilize its potential, but that doesn't mean you can't use it in the same way. So we have a gearbox, a motor gearbox driving a gear on which a linkage rotates, and then the linkage turns the rotational motion into reciprocating motion, and the large gear then drives a smaller gear on the light head assembly, which gives us the gear ratio to get our much larger oscillating arc. So here you can kind of see the whole picture. The middle gear there, that's the main drive shaft for the light, and it is a much smaller gear, so you do get that mechanical advantage. And this is what it actually looks like. So if we compare that to the motion that we were seeing, it makes sense. We've got the motor driving a series of smaller gears for drive purposes, and then the orange is the gear on which the rotating side of the linkage is. The green is the oscillating side of the linkage. and in the middle is the smaller gear getting driven by the larger gear that the green is on, giving us our full arc of oscillation. So everything seems to make sense. It just, it wasn't quite as interesting as I wanted it to be, but maybe that's okay. So we figured it out by looking at it, studying it, and actually getting partway inside of it. I didn't tear it apart, and it did look a lot like the way it was theorized. So the mystery was essentially solved. The light still does exactly what I've bragged about it doing. It has a super wide arc compared to its contemporaries, and it certainly is a unique piece of warning history. The question then becomes, why wasn't this adopted by Whelen on a larger scale? And why didn't other companies do this? Why were they happy with a 90-degree arc only flashing 2 of the bulbs? What was holding people back from actually using this technology more? And there is a good reason, in my opinion. We know that we are taking a rotational input and seeking to have an oscillating output. This little Lego contraption can represent our Rota-beam commander. This would be a motor with a gearbox for our rotational input. And then this is going to be our light head array with our oscillating output. On the back, we have a linkage, which if we placed our light heads on this spindle, we would get about 90 degrees of oscillation. But since we have them placed on this one, connected to this smaller gear, we're getting significantly more oscillation, a larger arc, which is pretty advantageous and worked really well, especially in like the Grimes light that was just powering a tiny little reflector, a little polished aluminum reflector going back and forth. You exchange a little bit of your power for a longer arc, which works really, really well in that case. And it works really well in the Rota-beam Commander's case too. But something that you run into is as the light head assembly oscillates, it wants to continue going in the direction it's going rather than reversing directions. And so that's just the propensity for an object to stay in motion and rather than reverse. So when we reverse, what's happening is this linkage is getting to the 12 or the 6 o'clock position in order to reverse. Well, at that particular time, that's when the oscillation switches directions. It also happens to be a time where you've kind of locked this gear mechanism because it's very difficult to overcome this little hump at the bottom of the clock, if you will, by putting a reverse input in. So the energy being transferred back into the system from the oscillating light assembly is going in the exact opposite direction that the gears are going to go. So the gears are going to pause and lock for a split second, and this is going to want to continue going in the same direction and then immediately reverse. So I really can't think of a more hazardous sort of condition to put gear teeth under. You are doing a dead stop and a reverse. And there's really no slip mechanism or anywhere to absorb that shock except the teeth of these 2 gears. And you've got this whole light head assembly with weight to it, momentum to it, going in a circular direction, and it wants to continue that way. And what you're telling it is, I'm going to lock up this gear system for a split second, and then I'm going to reverse it. So lock, reverse, lock, reverse, lock, reverse, lock, reverse, lock, reverse, lock, reverse. And it just keeps going like that. And it makes a nice wide arc of oscillation. but all of your stress is in the teeth of the two gears. And I have to imagine that is hard on even the most robust gear system. Um, I can think of some ways to mitigate that. Maybe like a slip joint type of clutch mechanism, something to absorb the shock of the reversal. Putting the spindle that the light heads are on, or the light array is on, kind of like a shock absorbing clutch or something. Um, uh, but I just have to imagine that while this worked great for the Grimes light to oscillate its little tiny aluminum reflector, to reverse directions on a large 4-beam cast bulb array, that's got to be a lot of stress on a system like this. And I'm going to speculate that that's why this particular system, while it did provide significantly more travel than the standard linkage that was used in the Beacon Ray 174, why it didn't catch on. I'm gonna just speculate that this was hard to maintain and had a high failure rate. Now, Whelen also did kind of get into strobes in the vehicle market, and the Commander strobe came out, and that using the same footprint as the Rota-beam Commander. So that may have something to do with the situation. But looking at this design, I really love the travel of the assembly, but I really have concerns for the stress being put on the gears due to the hard stop and direction reverse being directly absorbed in those gears. So the Rota-beam Commander showed up sometime between 1965 and 66 and only lasted a few years. And now we know how it worked, and I think we have a pretty good guess as to why it didn't stick around. We could say it was because of the rise in strobes from Whelen, or we could theorize that it's because it probably wasn't very durable and it probably didn't hold up. But I still maintain that I have one of, if not the last examples of the light, and that it was an interesting accomplishment, and they were ahead of their time looking at the ability to aim different colors at different sides of the vehicle. The idea that there should be no clear to the rear wouldn't come along for some time, but instead of just aiming a light at the sky like a hill light to take care of the clear problem, Whelen just let you pick 3 bulbs to show to any given side of the apparatus by making a 205-degree arc in the Rota-beam Commander. Hopefully that solves some of the mystery of what it was, why it was, and how it worked. Thanks for watching. Give me a like and subscribe if you are so inclined, and have a great day.